Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture Lecture Series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. My technological quest was for how and why parallel processing makes new computers faster and makes new supercomputers fastest. I began that quest on an old sequential processing supercomputer that was described as the first supercomputer. It was called the first supercomputer because it was the first computer that could record 1 million instructions per second. I began that quest on June 20, 1974, and I continued that quest on the then newly emerged vector processing supercomputer. In the 1970s, both scalar and vector processing supercomputers stood on solid grounds. However, the vector processing supercomputer that is faster than the sequential processing supercomputer was not a revolutionary technology. The massively parallel processing supercomputer was the hoped-for revolutionary technology. In May 1979, I entered into the uncharted territory of large-scale computational fluid dynamics. I reached the frontier of computational fluid dynamics and reached it with fast computers that were located in the Foggy Bottom neighborhood of Northwest Washington, D.C. In the mid-1970s, I described myself as a mathematician and as an astronomer. In the late 1970s, I described myself as a computational physicist. In the late 1970s, I was living in room 877 of Meridian Hill Hall at the corner of 16th and Euclid Streets in the Adams Morgan neighborhood of Northwest Washington, D.C. My supercomputer research of the late 1970s was a personal quest to discover how to solve computation-intensive problems that arose in large-scale computational hydrodynamics. I used massively parallel supercomputers to solve the governing differential and algebraic equations that simulate the flow of water within oceans, estuaries, and rivers. I used new massively parallel supercomputers to solve the 9 partial differential equations of calculus that I invented. I used new massively parallel supercomputers to simulate the flow of oil, water, and gas flowing underneath the surface of the earth. What made the news headlines was that I experimentally discovered how to simulate the motions of multi-phase flows flowing across porous media and how to simulate that flow across my internet. I visualized that new internet as a global network of 65,536 commodity off-the-shelf processors that were married together as one cohesive whole new supercomputer and married together by 1,048,576 bidirectional, regular, and short email wires that were equal distances afar and apart. As a computational hydrodynamicist, I used computers to compute the volume of water and the weight of suspended sediment loads that were flowing across a river. The knowledge that 197,400 cubic feet per second of water and sediment is discharged at a specific cross-section of the River Niger is needed and used to build a bridge across that cross-section of the River Niger. The sediment load of the River Niger at a cross-section is also computed and used to plan large-scale dredging of the River Niger. I can also compute the hydrostatic pressure forces, or the forces due to water at rest. The hydrostatic pressure forces act on the upstream cross-section of the Kainji Dam of the River Niger. The hydrostatic pressure forces was created by the 500 square mile Lake Kainji that is upstream of the Kainji Dam. In the mid-1980s, I was in charge of the standard operating procedures of 9 dams that were built and operated by the United States Bureau of Reclamation. The 9 dams included Alcova Dam, Glendo Dam, and Pathfinder Dam. Each dam was on the North Platte River in Wyoming, United States. However, I got known in 1989 for my contributions to how to parallel compute large-scale subsurface and atmospheric computational fluid dynamics. The specific fluid dynamics applications across a new parallel processing supercomputer or across a new internet that I am known for were on how to recover oil and gas and how to forecast the weather and predict global warming. The reason my experimental discovery was the cover story of the May 1990 issue of the widely read Siam News, the flagship bi-monthly news journal of the Society of Industrial and Applied Mathematics, was that I was a research large-scale computational mathematician who pushed the frontier of partial differential equations of calculus. I pushed the frontier of the calculus of porous media flow, or of fluids that flow below the surface of the earth. I pushed the frontier of that calculus from parabolic to hyperbolic partial differential equations. I pushed the frontier of the algebra that arose from that calculus and pushed it from small-scale algebra to large-scale algebra. I pushed the frontier of arithmetic to the fastest floating point arithmetical operations that can be executed across a new internet. I invented that internet as a global network of 65,536 processors that were equal distances afar and apart, and that I visualized as a small copy of the internet. I also pushed the frontier of calculus and did so by a distance of 36 partial derivative terms that were not in any calculus textbooks and that can be used by the petroleum industry to recover otherwise unrecoverable oil and gas. I experimentally discovered how to solve the most large-scale system of equations of algebra that must be solved to recover otherwise unrecoverable oil and gas. I experimentally discovered how to execute the fastest floating point arithmetical operations for large-scale computations in science and engineering. The reason my experimental discoveries in supercomputing made the news headlines in 1989 was that I was a supercomputer scientist who pushed the frontiers of the most massively parallel supercomputer. And the reason physicists invited me to give lectures on my discoveries and give them to the upper echelons of large-scale computational physicists was that I pushed the frontiers of large-scale computational physics. I gave invited lectures to large-scale computational physicists at the Ames Research Center of the National Aeronautics and Space Administration, NASA, in California. I gave invited lectures to large-scale computational physicists at the Los Alamos National Laboratory in New Mexico, the birthplace of the atomic bomb. I gave invited lectures to large-scale computational physicists in the research laboratory of the United States Geological Survey in Bay St. Louis, Mississippi. The reason I programmed the most massively parallel supercomputers and programmed them alone was that I discovered that as a polymath or a multidisciplinary scientist, I could work alone and propel myself into the elite ranks of supercomputing wizardry. After 16 years of supercomputing onward of June 20, 1974, I realized that I had more experience on massively parallel supercomputers and that I knew how to solve large-scale systems of equations of algebra and solve them at unheard of speeds. Looking back, I devoted 200,000 hours of my life thinking about new massively parallel supercomputers, which is 100,000 hours more than anybody else that I know did. And most importantly, my experimental discovery of massively parallel processing is one long, wide, and deep story rather than one short article. So, as a research supercomputer scientist, I had to understand the laws of physics and understand them above and beyond the state-of-the-art knowledge of physics in textbooks. I had to understand calculus and algebra and understand them above and beyond the state-of-the-art knowledge of calculus and algebra in textbooks. I had to have the deep understanding that informed me and enabled me to discover the century-old critical error that was in the system of coupled, nonlinear, and time-dependent partial differential equations that is the toughest problem in calculus that was used by the petroleum industry and used to recover otherwise unrecoverable oil and gas. Physically and a mile deep inside an oil field. The oil and gas flowing from water injection wells to nearby oil production wells was set and kept in motion by four forces: the temporal and the convective inertial forces, the pressure force, the viscous force, and the gravitational force. I mathematically discovered that for a century, the temporal and convective inertial forces were lost in the translations from physics to algebra to calculus and back to large-scale algebra and to the codes that had to be communicated and solved across a new internet that is a global network of equidistant processors. In the textbooks on initial boundary value problems on porous media flows, and in the textbooks on petroleum reservoir simulation codes, in those textbooks, a system of coupled, nonlinear, and time-dependent partial differential equations that is the toughest problem in calculus is used by the petroleum industry and used by ExxonMobil Corporation and used to construct their petroleum reservoir simulators. In each petroleum reservoir simulator, only 3 forces instead of 4 forces were encoded as partial derivative terms. In mathematical studies that I conducted in the early 1980s, I mathematically discovered that the 4th force, that was the sum of the temporal and the convective inertial forces, was missing and was not encoded into the partial differential equations used to recover otherwise unrecoverable oil and gas. And I corrected that error by inventing 36 partial derivative terms that arose from the second law of motion of physics that was discovered 3 centuries and 3 decades ago. I corrected that error by restating the second law of motion of physics and doing so correctly. I corrected that error by restating the algebra and doing so correctly, namely by restating the iconic formula F equals ma and restating it so that force equals mass times acceleration at all times and at all places within the petroleum reservoir simulator. F equals ma is the algebraic restatement of the second law of motion of physics that I will restate later in calculus. I corrected that error by beginning from first principles, namely the second law of motion of physics. I hit each law of physics squarely on its head and did so by demanding that inertial forces be encoded on and from the storyboard to the blackboard to the motherboard and across a new internet that I invented as a global network of 64 binary thousand motherboards. My correction of that error was the cover story of the May 1990 issue of the Siam News, the flagship bi-monthly news journal of the mathematics community. In the 1980s, I was logged on alone on the only supercomputer hopeful in the world that was powered by 65,536 processors. There was a digital divide with a twist. One black supercomputer scientist at the farthest frontier of supercomputing, and 25,000 nearly all white programmers on the soon-to-be obsolete conventional vector supercomputer side, or at the margin of supercomputing. I was logged on alone for two reasons. First, black supercomputer programmers were socially isolated and programmed supercomputers alone. I didn't know any other black supercomputer wizards in the 1970s and 80s. I knew from the unanimous rejections that I received from white supercomputing teams that a black supercomputer wizard will most likely be programming supercomputers alone and as an outsider. As an outsider, the black supercomputer programmer will most likely be thinking outside the box. For this reason, the black supercomputer wizard is fearless and raw and brings a diversity of ideas that's missing in all white scientific teams, and that each black supercomputer programmer will most likely be thinking outside the box. I will guess that about 25 of the 25,000 programmers were black Americans, and that five were black sub-Saharan Africans. As 1 in 1,000, the black supercomputer programmers of the 1970s and 80s were scattered and didn't know each other. As I got known after 1989, I heard from a few black supercomputer programmers. Each black supercomputer scientist reconfirmed my theory that he worked alone. He worked as a lone wolf. I'm a large-scale computational mathematician who became known for discovering how to solve the most computation-intensive problems arising in calculus and algebra and arithmetic, and invented how to solve them across a small internet that's a global network of 64 binary thousand processors. That's a new supercomputer de facto. I cannot describe equations that took me 16 years to develop in 60 minutes. Therefore, I've posted the details on my website, emeagwali.com. I also shared the abstract and invincible parts of my mathematical discovery on a mathematics lecture that I delivered at the International Mathematics Congress, ICM 91, that's held once every 4 years. My ICM 91 lecture was at 11 a.m. Monday, July 8, 1991 in the Dover Room of the Washington Sheraton Hotel in Washington in the District of Columbia, United States. I was invited by a society of societies named the International Council on Industrial and Applied Mathematics. The council asked me to speak at one of the ICM 91 symposia of the International Congress of Industrial and Applied Mathematics, that was a gathering of the who is who's in the world of mathematics, with many being at home with using partial differential equations of calculus to model and solve real-world problems such as general circulation modeling, to foresee otherwise unforeseeable global climate change, and petroleum reservoir simulation to recover otherwise unrecoverable oil and gas. To quote myself from that lecture that I gave to the International Congress of Mathematicians on July 8, 1991, quote, "Under the laws of physics is the partial differential equations of calculus. under the calculus is the system of equations of algebra. Under the algebra is a set of floating point arithmetical operations. Electronically and automatically executing the floating point arithmetical operations is a new internet. That's a global network of 2 raised to power 16 or 64 binary thousand processors connecting to each commodity off-the-shelf processor is 16 pairs of bidirectional, regular, and short email wires that were equal distances afar and apart. Controlling that new internet as a cohesive whole unit, that's a new massively parallel supercomputer that's comprised of 2 raised to power 16 processors that are married together by 16 times 2 raised to power 16 email wires is the new supercomputer wizard. I, Philip Emeagwali, was that new supercomputer scientist that was logged on alone to the only supercomputer powered by 2 raised to power 16 or 65,536 processors. The reason I am the cover story of today's June 8, 1991 issue of the Destroyed Free Press is that I experimentally discovered that the most computation-intensive problem in large-scale computational physics could be divided into 65,536 less computation-intensive problems that I solved in each of my 65,536 processors and solved at the speed of 47,303 calculations per second per processor. The total speed of my new massively parallel supercomputer was the world's fastest computation. In theory, a new internet that is a global network of 2 raised to power 64 processors will compress 585 billion years of time to solution to just 1 second of time to solution. The grand challenge problem of extreme scaled computational physics that consumes only 1 second on that new 64-dimensional internet will take 42.3 times the age of the universe to compute on only 1 processor. That discovery in the 64th dimension is my contribution to the greater understanding of the upper limits of the supercomputer that computes in parallel. That discovery of how and why parallel processing makes the computer faster and makes the supercomputer fastest is my contribution to the development of the computer. The reason I, Philip Emeagwali, was in the news headlines back in 1989 was because I discovered a new supercomputer that is not a new computer per se, but that is a new internet de facto. I'm Philip Emeagwali. Let's keep our conversation alive at emeagwali.com. Thank you.
insightful and brilliant lecture.